नहाने वाले
喂，是的，你好。我感觉应该是解决了，因为它秀完之后就没下过雨。好好好，感谢感谢。就是给给5星吧。
Hello, everybody. Welcome back to our data mining class on this lovely Wednesday night. I hope you all had a good week. All right, let's look at what we're going to cover today. But first, I think the add drop deadline is approaching. So you have your homework 1, right? So look at your homework 1 and really think about if you would be able to finish this class this semester. If you need more time, if you think you might need more, well, to be able, if you think you will need to learn more before you take the class, you can drop it and come back next time. No hurt feelings. All right. So do we have any questions about your homework assignment or about MapReduce? No one? So I think last time we were somewhere at the end of MapReduce. So let's just do a simple recap. Here you go. We talk about matrix multiplication, and we were here. All right, so when we talk about MapReduce, we are really looking at handling really, really large data set. So it's not 10 megabyte, it's not 200 megabytes, it's usually tens of thousands of gigabytes or terabytes. So your data sets should be huge before you even consider using MapReduce. Because as you can see in our MapReduce examples or in your homework assignment one, there are many different types of overheads included in the MapReduce process, right? You have to send data from one machine to another machine, and sometimes you have to send dummy values. Those can be time consuming, but those are the things that would enable you to parallel process very easily. So for MapReduce, we are really looking at large data set, and most real-world problems usually look at smaller data set. But it's a good idea to learn MapReduce and to be able to know if you need to process a large data set, you can use them. All right. Next slide. So other things about MapReduce is when you start to use MapReduce, your application should be the one that do not need fast response time. That means when you submit, well, for example, submitting jobs, Hadoop latency can be 1 minute. So you will never be able to get a real-time answer. So something that would require you to have a faster response time, like online purchase, transaction processing, these are not good for MapReduce. But MapReduce is a really good computation and pre-computation engine, which means if you want to run something overnight, then you take the result, you do online processing, you're good. Right, so let me give you one example. Say you're building a recommendation system, and our goal is to be able to find similar users to you so that we can recommend you stuff from that similar user. A pre-computation would be take 10 million users and group them into smaller clusters. So when the new user comes in, we can identify that cluster and then we do recommendation, right? But your pre-computation, this clustering, it can take weeks. It's okay. We don't really need that result in real time. MapReduce is also good for applications that work in batch mode. That means you want to run over the entire data set. It really takes time to run. If you have 100 terabyte of data set, shuffling step can be also time consuming because it needs to be able to read the keys from map results and then decide which machine it has to go for the reduced steps. We do not support random access to data sets in MapReduce. There are some extensions, but in general, if you want to do random access, that means you have to have some index of your data set. And if you remember, doing MapReduce, we do not have any index. So general characteristics of good problems for MapReduce: works for data that can be expressed as key value pairs without losing context or dependencies. So for example, if you have graph data, nodes, link, this will be difficult to be represented as key value pairs. So graph data is not really something MapReduce would be able to handle well. There are other alternatives that you can use for graph data. Some other problems that are not suitable for MapReduce: tasks that need results of the intermediate steps to compute result of the current steps. So this means you have some interdependencies between tasks. So remember when we are doing our matrix multiplication, each node or each component here in the resulting matrix is independent from each other, right? So you can do parallel processing. However, if some data set you do have the dependency, it's not really a good idea to use MapReduce because you cannot really use that parallel processing power. Some machine learning algorithms are not very good for MapReduce because the same thing, you have dependencies between tasks and you need one task has to wait until the other task has finished so that it can start. So just in summary, good candidates for MapReduce would be the jobs that process really large data set. And the goal for your MapReduce task or tasks is usually to summarize your data or transform your data. So think about this data processing pipeline, input, output, and you have some analytic method. I'd say this could be some algorithms to identify interesting patterns. Okay, could be a machine learning algorithm, could be a data mining algorithm. But before your input data can be used in this process, very often you have to clean your data, right? You have some missing values. How do you deal with missing values? Sometimes you have to transform your data. You want to do aggregation. You want to take two values, add them up, and subtract the third value, right? So all these processes are very good for MapReduce. Some data mining process is very good for MapReduce, but most of the machine learning task has independent subtasks, so they are not very good for MapReduce. Collected data has elements that can be easily captured as key, and values will be good for MapReduce. All right, that's everything I want to say about MapReduce. Any questions? Let me upload the slides for the next topic. Okay, you should be able to find our next slide set on Piazza. Right, so there's a question for graph databases. The objects represented as JSON object, so would that not be a key value relationship? Yeah, you can still do key value relationship on a graph data set, but the real problem is now it becomes very difficult to find a matching node. So let me show you. So for example, in a graph data set, you are usually having something like this, right? So it could be a Facebook friendship graph. This is you, these are all your friends. And of course, we can use key value pairs to represent it. We can say node I has a friend J, I has a friend K, and so on. But the real problem is most of the graph algorithms or what you want to do on graphs will require you to identify this relationship quickly, right? So you want to traverse from this node to, well, ij from this j node. J could have a friend of O, right? So you want to traverse this relationship, but the key value pairs, you cannot really do that. Maybe this key value pairs is in your map task 1, this one is in your map task 2, so it becomes really complicated. All right, so the second topic, now we are going into the algorithm part, and I really love this topic on frequent item set. And this year we got some new algorithms that I really want to show you. So here's some questions. So question, when you say tasks that need results of the intermediate steps to compute for the next step, do you mean highly serialized problems like computing Fibonacci series? So yes, but think about this. You have your map task, right? You have your reduce task. And we are assuming that your reducer would be able to work independently, right? This reducer does not have to wait until this one. So reducer 1 does not have to wait until reducer 2 finish before it can start. So that's the dependency. When we say, well, like you said, highly serialized problem or problems that require intermediate result, usually means this reducer will need to be the reducer on the left, reducer 1. Reducer 1 needs to wait until all of the map tasks have finished before it can start. So that's not really a nice parallelizable problem you want to work on. All right. Frequent item set. It's good you guys are asking questions, because or it will be only me talking to the screen. All right, finding frequent item set. Remember to read your textbook, chapter 6. So finding frequent item sets and association rules is our main topic for this week and the next week. We are mainly focusing on finding very interesting pattern called frequent item sets. For example, this will be sets of items that are frequently purchased together, for example, in a supermarket. But frequent item set algorithms can be used in many, many different cases. They are not limited to supermarket transactions. So this will be our outline. I'm going to talk about this market basket model. Then we're going to look at several algorithms. Oh, and this will be your homework assignment too. First, market basket model. So our ultimate goal here is to identify something called association rules. And what are association rules? In this example, we are looking at supermarket transaction data. And our goal is to be able to identify items that are purchased together. So together is the key here, by sufficient many customers, okay? This statement is actually very interesting. So what does it mean by sufficient many customers? Well, this implies that we will have a hyperparameter that help us to say, all right, S is our parameter if an item or two items are bought together by more than S customers, we say it's a frequent item set. And our approach is to process the transaction data or sales data to find the dependencies among items. Okay, so this is very important. We're looking at relationship between items, not transactions. So for your physical stores, we are going to use data that are collected using barcode scanners, right? When you go to a supermarket, they have this barcode scanner, so they know what you have purchased in one transaction. For online retailers, this is very easy. They have all the transaction records, and they'll be able to take the transaction records and figure out that information. So let me try. Sorry. Something's wrong with my Zoom. Okay, so a classic example, it's if someone buys diaper and milk, this person is highly likely to buy beer. So think about this. How do we know this? Well, if you're running a local grocery store, you will sit there and watch people's behavior every day, right? So eventually you get the sense about what are the items that are frequently purchased together. But we are not just running a local grocery store, so we're going to use data collected from machines. And if you look at this rule, these are relationships between items, right? Not transactions or not customers. So based on these rules, we can do all kinds of sales technique. For example, if we put 6 packs of beers next to diapers, this might help us to boost the sales because we know that if people purchase this, it's highly likely they will want to purchase beers. So you put them next to each other. So let's look at an example. Remember, we did this before. I said, always ask for input, process, and output, your IPO. So in mining frequent item set, our input is always a large set of transactions. And it usually look like this. It can be a database tables, but because these transactions are usually huge, so it usually in a flat file. So it's a large file. So let's see if there's a question. So if you look at the input, each row here is a transaction. Okay, so that means a customer make a transaction, and in this transaction, this customer purchased bread, Coke, and milk. And this is the next transaction. Doesn't have to be the same customer, and you don't have timestamp. The output is an association rule or multiple association rules. So this will be the rules that we discovered. Milk implies Coke, right? If someone purchased milk, that means this person would highly likely to purchase Coke. If someone purchased diaper and milk together, this means it's highly likely to find beer in that transaction. So a few assumptions here. We have a large set of items. This will be all the items you can purchase from the supermarket or online store. So given the example here, how many items do we have? Anybody? How many different types of items do we have? 5. So someone says 5, let's try. Bread, Coke, milk, 3, 4, diaper, 5. Right, if you're Amazon, the number of different types of items that can be in a transaction would be millions. And we do have a large set of baskets. If you only have 5 baskets, it's not going to work. So we're talking about millions of transactions. Each basket is a small subset of items. That means each transaction will only cover a few items here. So this makes sense, right? You won't expect that your customer in one transaction will purchase 100 different types of items. It could be 100 items of the same type, but the number of types will be small. And we want to be able to discover the association rules like the output here. Will be people who purchase this would highly likely to purchase this. And there will be many applications for this, right? We talk about this price manipulation. We also talk about recommendation system, right? So if someone purchased milk, you would just recommend, hey, do you want to buy some Coke? So in this market basket model, this is really a many-to-many mapping, and this is called association between two kinds of things, items and baskets, right? Remember in that table, you have many baskets. Each basket, you have many items, well, a few items. But we are actually looking for connections between items, not the baskets. So just remember in your association rules, it's always about some item or items imply some other item or items. And the technique that we are going to cover in the lecture or for this mining frequent item set algorithms, we focus on common events, not rare events. Okay, we are not going to look for outliers. We are going to find commonly happen patterns so that we will be able to use that to our benefit. And we are not focusing on finding all association rules. We want to focus on common events. And we're going to talk more about this later when we talk about the algorithm. So let's look at some examples that you can use mining frequent item set algorithms to solve. Say the items are products, your baskets are a set of products someone purchased together in one trip to the store, right? This is our very basic supermarket example. So in a real supermarket, your store will keep terabytes of data about what items customer purchased together. If you have been to Walmart, you know they have a lot of customers, and that would translate to lots of transactions. Walmart actually have a Walmart lab doing very interesting data science stuff in the Bay Area. So check it out. So all this information, this baskets tell us how typical customers navigate the store. So we focus on typical here because we want to find common event, not rare event. So the store would be able to use this information to position tempting items or do some tidying tricks, put diapers on sale, raise the price of beer. And to be able to do this, we will need the rules or the patterns to occur frequently, or we will not have profit, right? So this is a very good example that you want to find those common patterns, not rare events. Or if you think about Amazon recommendation systems, it will tell you that someone who also purchased X would also purchase Y, right? This is a common pattern. Okay, so this one is easy. Let's look at the next example. So if we want to do plagiarism detection, we are going to have a bunch of documents, right? And each document will have a bunch of sentences, and we want to find this common pattern. If we want to use our market basket analogy or market basket model to model this problem, what would be our basket and what would be our items? Well, in the previous example, it sounds pretty easy, right? Because the basket is the basket, the items are the items. But in this case, we have document and we have sentences. So we need to be able to assign the documents as baskets. If you do document as basket, it looks like this. All right, so document 1 contains sentence 1, sentence 2, document 2 also contains sentence 1, and sentence 5, and so on, right? If you use sentence as document, you would say sentence 1 appear in document 1 and document 2. Sentence 2 appear in document 1. Okay, so this is just different representations of the same data set, right? So what do you guys think? We have some answers in the chat. Basket is the document, items are the sentences. Okay. Any more people wants to answer? All right, so before I tell you the result, let's think about this. Our goal in plagiarism detection is to find relationships between what? Between documents or between sentences? We say, all right, you have two documents. These two documents appear to be very similar, so we detect plagiarism. All right, great. You guys are saying documents. So we are actually detecting, want to identify relationships between documents. Awesome. Remember our market basket algorithms, we say we are looking for a relationship between what? Between baskets or between item and baskets or between items? Anybody? Remember that milk, diaper implies beer. This is relationship between what? Items, baskets?
Items.
Between items. Awesome. So, all right. If our application asks us to detect relationship between documents and the market basket model is going to detect relationship between items, then you should model your documents as items in your sentences as baskets, right? So let's show you. Let me show you how this works. So your items is in the basket if a sentence is in the document, right? So it becomes this. Sentence 1, document 1, document 2, and so on. Sentence 2, document 1, document 2, and maybe document 3, and sentence 3, and so on. So if two documents appear together in many sentences, what does it mean? Well, it means these two documents share many of the same sentences, right? So that's your plagiarism detection results. Just remember, this is not a very good plagiarism detection algorithm because using sentence is too coarse. It's really difficult to, well, if people change one word, you will not be able to capture this relationship. But this example is really great because it forces you to think about what type of relationship you are detecting and who should be the basket and who should be the items. Awesome. So next example, we want to identify related concept in web documents. So concepts here could be a set of words, right? So if you have a set of words, they become a concept. Web documents are those documents that contains all these words. So what would be our baskets? What would be our words? All right, related concepts. So this is the relations that you want to identify, and your algorithm will identify relations between items. So your words should be items. Your baskets should be your web page, items and words. Your words should be the items. So we are going to look, well, this means we are going to look for a sets of words that appear together in many documents, and this becomes some concepts. So for example, if we look at the word world and the word cup, they appear very often together in many documents. We can infer there is a concept if you put them together, right? Word cup can be a concept if many of documents contain word and cup appear frequently. So the next example would be drug interaction. You have a bunch of patients, you have items that are drugs and side effects. That means we can do this. Patient, drugs, drug, side effect, second patient, more drugs, more side effect, and so on, right? So this can help us to detect commonly appear together, the drugs that are commonly appear together, or the drug and side effect commonly appear together. So this is really cool. We will be able to detect combination of drugs that result in particular side effects. However, there's one thing that's very important. Absence of an item should be considered in this case, because, for example, if you say, all right, this drug commonly appear with this side effect, right, based on all your patient data set. However, you might notice if we add one more drugs, like for the patient that have this drug X together with this first drug, you will not see this side effect, right? So you will need to be able to capture the absence of an item set. So this requires some extension that we are not going to cover in this class, but it's a really interesting problem to look at. All right, so what is the scale of the problem? Remember at the beginning, we talked about large data set. So the scale of this problem, if you look at Walmart, 100,000 items is the number of different types of items that can be in a transaction, and they can store billions of baskets. And the web would have billions of words and many billions of pages. So lots of item types and lots of baskets. Still, remember, each basket only have a few item types. And the number of items is not important. So if someone purchased apple, orange, 5 apples, 2 oranges, not important. We are not going to look at this, okay? That will be for other algorithms. All right. So that's an overall view of this finding frequent item set and association rule problem. And I show you a number of applications. Now let's look at the definition of frequent item sets. Remember, we talk about sufficiently large number of customers. To define a frequent item set, that means we want to find, well, to find frequent item set means we want to find sets of items appear frequently in the basket. This tells you that you have to define frequently, but we are computer science, not social science. So you have to be able to quantify them. Nothing against social science, they're great. So support for item set I is our threshold for defining frequent item set. And a support is the number of baskets contain all items in I. And sometimes we would just use a percentage, right? What's the percentage of baskets contain this item? And if we have a support threshold S, we will be able to say for an item set I, if your support is larger or equal to S, then you are frequent item set, okay? So the keyword here that you should remember is support and support threshold. And I'm going to use one example here to help you. Say this is your item set. 1, 2, 3, 4, 5. You have a total of 5 different types of items that you can sell to your customer. And we have a support threshold, 3 baskets. What does this mean? If milk appears in 3 or more baskets, then we say milk is frequent purchased item. So let's look at all your baskets. How many baskets do we have? 8. Great. So what are the frequent item set of size 1? MCBJ. How do I know? Easy. I count them. So I initialize a counter for every item type I have here. and I read the first basket, I say milk. All right, counter 1, Coke 1, beer 1. I read the second data set, milk 1, Pepsi 1, juice 1, and until we read the last, until we finish the last baskets, then we have all the counts, right? So based on this, what is the count for M? 1, 2, 3, 4, 5. 5 is greater than 3. All right, frequent. What's the frequency? What's the support for C? Anybody? Five. B. 1, 2, 3, 4, 5. J. 1, 2, 3, 4. What else? We have Pepsi. What's the support for Pepsi? 1, 2. Okay, this is difficult. All right, 2. So based on this and based on your support threshold, we know that Pepsi is not frequent, and we know all others are frequent, right? That will be your M, C, B, J. And let's look at what are the frequent item sets that are, what are the item sets that are frequently purchased together? We have our M, B, M and B, 1, 2, 3, 4. B and C, B, C, B, C, B, C, B, C also 4, and do that for CJ and so on. And this becomes your frequent item set of size 2. Okay, because their support is larger or equal to your support threshold. This means they are frequent. So what have we learned from here? Well, we learned a couple of things. Well, first, the algorithm is very simple, right? You just count stuff. Then you will be able to know if an item is frequent. And when we count stuff, your counter becomes your support for certain item sets. And you can have item sets of size 1, which means single items here. You can have item sets of size 2, which means pairs. You can actually have item sets of size 3, for example, M, B, C. So let's count it. How many items do we, how many baskets contain MBC? Is it frequent? MBC, okay, so people are saying 2. All right, 2. So is it frequent? No, it's not frequent because the support of MBC is 2 and the support threshold is 3, so not frequent. Awesome. Okay, so question, do we choose frequent item sets of size 2 based on the item sets of size 1? That's a really good question. That's our algorithm, and we're going to talk about them later. But here is just to help you understand terminology in the data set that we are going to use. All right, from the frequent item sets, we are able to then generate association rules. So these association rules are actually our final output. So just pay attention to the association rules because we are not going to cover them. We're not going to cover too much of them. They are not very complex, but we're going to cover algorithms to count frequent item sets. So these rules are if-then rules about contents in a basket. So for example, if your baskets contain all these items, and if we have a rule like this, this is your association rule. And this rule says if you see all these items, it's likely this basket will also contain J. Okay. So what does this mean, likely? Well, if people tell you likely, we will need to ask this person, how likely, right? How do you quantify it? How do you know? This is our confidence score. So each of the association rule will come with a confidence score. So this confidence score tells us the probability of seeing J in the same basket, given that you have all other items, right? So this is the first part of the rule. This is the second part of the rule. And it's very simple. It's the ratio of supports for the union. Union is this and J divided by the support of I, right? Basically, in English, this is saying that given all the baskets that contains your evidence is this. How many of them contain your evidence plus J, right? So this is your confidence. And let's look at an example. Again, our old friend, 8 baskets. You have association rule like this, assuming you identify an association rule. The confidence is the ratio of this and this. What is this now? So I union J would be MB and C, right? This is I, this is J. So the support of MBC will divide it by the support of MB. You will be able to generate the confidence. Okay. Okay, so there's a question. Is support of an item the same as count of an item? Yeah, support is just count, frequency of an item. So how many baskets contains M, B, and C? 1, 2, 2. Okay, so this is 2. How many baskets contain MB? 1, 2, 3, 4. So this is 4. So your confidence is 50%, right? It's pretty obvious. This is telling you that for all the best, since you are going to show me this rule, you say this is highly likely. I say, all right, what's your confidence? You will say, all right, 50% of the time, if you see MB, you will see C. Okay. It's not very high. So this is not a very high confidence score, but this is to show you how you will be able to calculate the confidence score. All right. So other than the confidence score, we also care about another score called interest score. This is because not all scores not all association rules that have high confidence are interesting. But what does it mean, interesting? So the rule X implies milk may have really high confidence because every time when you see X, you will see milk. Because milk is just purchased very often, say 90% of your transactions contain milk. And this makes this rule less interesting because it's very obvious and you might not be able to benefit from having this rule. So we want to be able to generate a score to help us understand how interest a rule is. So the interest of an association rule is the difference between its confidence in the fraction of the baskets contains J. What does this mean then? Well, the formula is this. Very simple. You know how to calculate confidence. You just need to look at this, okay? So this tells you without looking at any of the rule, how likely would J be in the basket, right? This is your prior knowledge of J. And interesting rules will be those with high positive or high negative values, and usually between 0.5. What does it mean then? Positive means the presence of I would encourage the presence of j. Okay, j here, I here. If you have large negative value, it means the presence of I would discourage the presence of j. So one example would be someone purchased Coke. This person would highly likely purchase Pepsi, and it should have high negative interest. Okay, so let's look at how we calculate it. We know, well, our old friend again, and B implies C. We know how to calculate confidence. Awesome. 0.5. So interest is your confidence here. Subtract by the probability of finding J. So how do we calculate this value? So how many baskets do we have? 8. And how many of them contain J? 1, 2, 3, 4. So this should be 4 over 8. Something's wrong here.
I think we're supposed to be looking at C instead of J.
Okay, yeah, right. Sorry, C. Great. Someone is paying attention. This should be C. So how many baskets contain C? 1, 2, 3, 4. Still 4? 5. All right, so it's 5 over 8, and you have 1 over 8, and it's not very interesting. Okay, it's a very small value. So now we learned that you have 2 ways that you can quantify your association rules. For example, this is your rule. You can generate confidence value, and you have interest value. So if we look back, think about our previous example. You want to track 1 billion people. You want to find suspicious pairs of people, right? And our result is 250,000 pairs of people, and we say this is not very useful, all right? And if you look at association rules, let's say if you generate this number of rules, and then it's not very useful. However, in this case, you can calculate confidence, and you can calculate interest, and you can use them to rank your association rules. Then you'll be able to pick the top ones and work on them, right? So this will be very nice once you will be able to calculate this too. So question, how do you have negative interest if you're taking absolute value? Yeah, usually you don't. Good catch. All right, 6:52. Let's take a 10 minutes break. Come back on 7:02. If you have any questions, post it in the chat. I will answer them when I come back. Hello, everybody. I'm back. Right. I think there is a question. The question is, can you explain negative interest in maybe an example? If you look at here, how we calculate interest. Here. And here. And also here. Okay. To have a negative value here, which means you can have a really large number here. So for example, using that Coke Pepsi example, let's say Pepsi is very popular. So 80% is this probability. 80% of the basket contain Pepsi. And we're looking at Coke implies Pepsi. What is this? Well, this is the confidence, right? So how confident are we when we look at this rule? So this means you are looking at the support for Coke and Pepsi divided by the support for Coke. And we expect this value to be very low, could be 10%. 10% support means 10% of the basket contains, well, only 10% of the basket that contains Coke will also contain Pepsi, okay? So if you have 10% here, 0.1, 80% here, 0.8, you have a negative value, 0.7, and this tells you something. This tells you that if you see Coke, it's unlikely that we'll be able to see Pepsi, and this could be an interesting rule, right? High negative values is interesting. All right. Often they are mutually substituent items. Yes. All right, look at association rules. So now you know what supports are, you know how to calculate confidence and interest. Our real goal is actually to find out association rules with support larger than a threshold and confidence larger than a threshold, right? Because you have to decide what do you mean by frequent, and you want to also talk about confidence. The most difficult part well, you might also have an interest threshold. The most difficult part here is not generating these rules. The most difficult part is to find frequent item sets, which means you have to count them. So for example, if we look at this rule, let's say this has high support and high confidence, then this has to be frequent, right? Means this has to appear many times, and this union has to appear many times. We will look at one example on the next slides, so don't worry. We assume that there are not too many frequent item sets or candidates for high support, high confidence association rules, so that we will not have too many of this here. And if we don't have too many of them, we will be able to act on them, right? It will not be like your 250,000 pair of people example. And if eventually you found so many of these rules, you will need to adjust your support threshold to avoid too many frequent item sets. What does that mean? Let's look at here. Our friend 8 baskets. We have support threshold. We have confidence level threshold. This is all your frequent item sets. All right. How do we find the frequent item sets? Anybody? How do we know B is frequent?
It occurs 3 times or more.
It occurs in three baskets or more, right? 1, 2, 3, 4, 5, 6. How do we know BM is frequent? Well, the same thing, right? You look at BM, 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 and so on. So great, we have frequent item sets. To have frequent item set, what do you need? You need a support threshold, and you need to count item sets. Based on the frequent item set, we can start to generate rules. So here's a question. How do we generate rules? Based on all the examples I show you, can we generate a rule from B? Remember, our rule is always something, some items imply some other items, right? B is frequent, doesn't really tell us anything, so we cannot really generate any rules because you cannot say B implies B, right? This is obvious, we already know. How about this? Frequent pair. What can we generate? Okay, somebody says we can generate B implies M. What else? One rule from one basket. Great. M implies B. Okay, so one thing that's important here is we are looking at item sets. So the order is not important. You have BM as frequent. That means you will be able to test if either this rule or this rule that have a high what? What are the things we want to test to fulfill our goal? What is our goal? Find association rules that have high support, high confidence, and high interest. So what's the next step? What are the things we want to try? Test on these two rules? Well, you need to test their confidence and interest, right? Okay, great. So now we know that you can generate 2 rules from BM. What about MCB? How many rules can you generate? Anybody? Okay, somebody says 6. How do we come up with 6? M implies C and B. MC implies B. What else? MB implies C. CB implies M. More? BM? We already did BM. Anyway, I think you got the idea. On either side, you can have more than one item, and you can generate many rules. All right, let's look at here. Now we can generate all kinds of rules, and you can generate their confidence, you can generate their interest, and you can use thresholds to remove the one that you don't like. This is pretty cool, right? Now you have the association rules, and you can start to use them. What's the most difficult part in this process? If you have the slides, the most difficult part is identifying frequent item sets here. So let me ask you this. If you look at here, this involves 2 computational steps, right? 1, frequent item set, finding frequent item set. 2nd, generate the rules. Well, maybe we can add the 3rd step is to generate all the confidence values. So why are we saying that this is the most difficult step? Anybody? Or most challenging steps? This is just counting stuff. How difficult can it be? All right, I see. Good answer. Okay, data is big, yes. And we need to check all combinations of items. within the baskets. Great answers, guys. So if you look at this process, remember input, process, output. What is the input? Your input is all the baskets, right? And we say we can have many, many baskets. We can have 8 billion baskets. And we can have many, many item types. You can have 2 million item types. So counting them is actually not easy, not a simple task. Although counting, count their occurrence is not difficult, but when you have many, many of them, it becomes an issue. If you don't do it right, it will become very, very slow. Or you can use MapReduce. But still, we need to be able to handle large data set. And how about this step? Well, remember we said that if you have a good support threshold, not that many item sets will be frequent, right? So if you don't have many frequent item set, the input for this step will not be really big data. And it's super easy. You just do the permutation, generate the rules, and to generate the confidence and interest value, because you already count them. You already counted them when you are doing frequent item sets. So you will be able to just calculate them. Okay, even if you have to recount them again, now you don't have that many item sets that you have to count. So easy. So from here, from these slides to the end of this topic, we are going to focus on algorithms that can help us find frequent item set very efficiently. We are not going to talk about their association rules, confidence, and interest, but always remember our goal is to identify association rules that have high confidence and high interest. This will appear again in your quiz and in your exam, just to make sure that you will not focus only on the algorithms of finding frequent item sets. All right, finding frequent item set algorithms. Okay, so someone's asking how to determine support threshold. We're going to cover that, but like many questions in data mining is it depends. What does it mean it depends? Well, in practice, if you have 2 terabytes of data, you would do a random sampling first. You take 200 megabyte data and you try different support threshold on your small data set. Once you find one that you like, one that will not generate too many association rules, you use that for your entire data set. Okay, so always do sampling. All right, let's look at find frequent item set algorithms. So our computational model. Typically, your market basket data are kept in flat files, not in a database system, because this is really huge. So you don't want to use a relational database to store them. People usually store them on disk because these are very large file. Remember in our previous lecture, this will be on a distributed file system, right? So you can have multiple machines to count them at the same time. And they are usually stored basket by basket. And our goal would be to expand the baskets into pairs, triples, as you read them, so that you can count them. You will need a k-nested loop to generate all sets of size k. What does it mean? Let's look at next slides first, then I will explain that. So this is your typical market basket data. And here, think about this is a really large file stored on some distributed file system, but as your when you write code to interact with this large file, you usually don't care, right? It can be stored in multiple parts, but you don't know. Your code doesn't have to cover that, does not have to handle that. And in the file, in this case, every row is an item and a bunch of rows is a basket, and you usually have something in between baskets, maybe an empty line or a -1 as the item ID to indicate that you are going into the next basket. So what does it mean to count stuff? Maybe I should use the whiteboard. Let me try it. Okay, so remember in our previous example, we are looking at Coke, diaper, juice, Pepsi, right? And oh, I should write it as a set. Just to make sure that you remember the order, it doesn't matter. And we have many of this. And it's stored in a flat file. It could be that this is one row, or this could be that you have C, D, J, P, and -1, and then so on, a second basket. Great. So our goal is to count their occurrence, right? We say it's the support for your item sets. And we say that, all right, to look at your item sets, what are the item sets we have? We can have C, we can have D, we can have J, we can have P. Just to say these are item sets, let's put this set notation around everybody. What else can we have? Well, this is your single item sets. You can now have pairs. You can have C, D, C, J, C, P, and you get the idea, right? Okay, great. So if you want to write a program to count the support or the occurrence, it's the same thing, of all these things, what's your first step? Anybody? No one? Isn't this a super easy task? You have a file, you want to count this, you write your program in Python. What's your first step? What's the first step in your algorithm?
Count the number of singles that reach the support.
Well, before you can count them, what do you need to do? Okay, great. I see an answer. Read line by line. So always remember when we are talking about all these data mining algorithms, all these small things becomes very important because you have to do it many, many times. So we need to read the file, right? That's always your first step because you have no idea what are the data sets or item sets you have to count. So you read the file. Now you know your first basket. It's C, D, J, P. What's your second step? You read it. You want to initialize counters so that you can count them, right? How many counters do you need? What would be a good way to initiate a counter? How do you count this? Number of all items? For loop. Okay, you guys are close. For using dictionary. All right, dictionary. Great. Let's look at how dictionary works. So dictionary, again, you have key value pairs. What would be your key? Anybody?
Item, yeah.
Item sets, right? So you can have C, you say I see C, and what will be the value here? 1, great. C1, D1, J1, P1. Are you done with the first basket? Okay, so somebody says CD, great. So you have to do CD and 1 and so on, right? So this means for single items, you have to use a for loop to loop through I till the end of the basket length. And to generate, this is only to generate this. And to generate the second set here, these are the pairs you have to do for loop twice, right? The first one is looping through CDJP. The second one is say, all right, now I have C. What would be the next item that I can add as my pair? So that's D. So that would be here. What does this mean to you then? Well, this actually tells you that without really looping through all the items in the basket, without really looking at all the items, you do not know what are the things you have to count. Okay. So unless you do 2 for loop, you do not know what all the pairs that you will need to count. What if you want to count triples? In this case, we want to count CDJ and we say CDJ1, right? Because we see CDJ once in this basket. If you want to generate a counter for this, what would be the for loop you have to do? Well, you have to do 4, 4, and 4. So time complexity is a problem, but it's really not a huge problem because you don't have that many items. But the real problem is to be able to count them, we have to initialize a counter, right? So in this case, when we do CDJ and we look at here, we say, okay, we will need to count it and give it a 1. Okay. Then to be able to count CDP, you have to have your 3 nested loop will need to loop through CDJ, then you will be able to initiate a counter. Okay, and this way you will be able to count everything, initialize a counter for everybody. So this becomes important later, but let's look at the slides. Okay, great. So this is what the slide is telling you. We want to be able to find. We want to be able to find frequent item set. We want to be able to find frequent item sets. So we need to count them. To count them, we need to generate them, right? If you are using a dictionary, that means you have to generate a key and initialize the value to 1 if this is the first time we see it. If it is not the first time, we just add 1 to this counter, means we see this again. So the true cost, because somebody's asking for time complexity, very good. The true cost of this, or the frequent item set algorithm that we're going to talk about is the number of disk IOs. So in practice, association rules algorithm will read the data in passes. This means this is your basket data. For 1 pass, you read the entire file and you count something, then you read it again, okay? And when we say read in a pass, it's a very expensive disk IO. So we're going to measure the cost of the algorithm. We're going to evaluate our algorithms by the number of passes that an algorithm needs to be able to count everything to find all frequent item sets given a support threshold. For many frequent item set algorithm, the main memory is the critical resource because as we read your baskets, we need to be able to count something, and the number of different things we can count is limited by the main memory. because we do not want to swap pin counts in and out from your disk. And your algorithm is designed so that the count will be able to fit into the main memory. This might sound very abstract to you, but let's look at our previous example. When we start to count all these baskets, what are our memory usages? Which part do we use memory? Anybody? Let me give you one. You have to read line by line, right? So of course you are going to store one basket in your memory. What else? Well, when you read the next basket, you can throw this one away. But what else do you want to store in your memory? Counts. Great. Thank you. That's your dictionary, right? Your key value pairs. This thing will live forever in your memory until you finish counting. And by swapping counts means when this becomes too big, you might need to store some of them into your disk and then read them back and then store them back to the disk. And this is very, very time consuming. So we want to avoid this. This means we want to initialize the minimum counters we need to be able to count everything. So in finding frequent item set, the most difficult problem is usually finding the frequent pairs. And this is because frequent pairs are common, frequent triples are rare, right? Having C and B occur frequent could be pretty common, but having something like C, Coke, beer, diaper, milk, and Pepsi all in the same basket and become frequent, many baskets become frequent, this is highly unlikely. The probability of being frequent drop exponentially with sizes. Number gets grown more slowly with sizes. This is heuristics, which means from people's observations, this is usually true. So our algorithms are going to concentrate on pairs, but you can see how, I will show you how we will be able to extend this to larger item set. So larger here means frequent pairs, you have 2 items. Larger means you have more than 2 items. Could be C, B, and K. Okay. Let's look at the naive algorithm. So a naive algorithm to solve this problem would be to count everything, right? You read the file once, you count in the main memory the occurrence of each pair. Remember now we are focusing on pairs. Still remember this? The number of pairs in the baskets of n items. Well, if you are counting for frequent pairs, very often you already know how many different types of items you can have, right? For Amazon, this could be millions. So the number of pairs in the basket will be n choose 2. And we say when n is large, it's close to this number of pairs. Okay, so this means for each basket of n items, we will generate these pairs using 2 nested loop added to the counter. First basket, look at here. This will be all the pairs that we can generate. Remember the 2 for loop on the whiteboard. Second basket, we generate this. Total number of pairs in all basket could be the number of items times the number of items minus 1 divided by 2 because it's C. Number of items, choose 2. And if you're a Walmart, this could be really big. If you're processing the web, this can be even much larger. Let's look at one example here. Suppose you have this many items. Every count requires 4 bytes. Number of pairs of items, 10 to the power of 5 choose 2 is this 5 times 10 to the power of 9, and this times 4. So you need 20 gigabyte of memory. Are we good so far? Let's look at this one. And think about how you should store your memory counters. All right, 2 approaches. If you have all these items and we know we have this number of pairs of items, what we can do is we can pre-generate a hash table, use 20 gigabyte key value, and set every value to 0. Right? For example, let's say all your items are, each of them has an item ID. So from 0 to 1 to 2 to 10 to the power of 5 minus 1. Are we good so far? Are we okay? No one? Okay. This is all your item ID, and you can pre-generate this table to store all the counters. And your key would be what? Now we are counting pairs. What would be your key? Anybody? Great, thank you very much. That would be each pairs, right? So you have 0, 1, 0, 2, 0, 3, and so on. Because you already know this, so you can use the for loop, a nested for loop, to pre-generate this for 20 gigabyte. Is this a good idea? What would be the problem of this? What would be a problem? Yeah, well, you have to use 20 gigabyte, but what is the problem that we think this is not a good idea? Too large memory is not enough. Yeah, but there is one very interesting thing. All right, we have a winner. Yes, we might not need all pairs, right? So for example, without looking at the basket, you just generate all pairs from your item types. Many of this can be 0, okay? Then because 0 and 1, they just never exist in any of the baskets, and you are wasting some of the pairs, some of the memory space. So this leads to our next topic. How do we store your counters, right? If you're working on a small data set, this is a trivial problem. You just use an array, you use an NP array, you use a list, a hash table. You don't really see the problem here. But when we are talking about large data sets that you can have billions of pairs, this becomes critical. So 2 approaches that we can do. We can count all pairs, okay? Or we can keep a table of triples to count pairs of items. So let me tell you the difference here. To count all pairs like we did before, it will require, I'm going to explain this, but just look at the requirements first. If we are going to count all pairs, you are going to need 4 bytes per pair. However, it requires you to initialize a counter for each pair, right? Remember, sometimes some pair they will not appear together, so you are losing counters. You're initializing counters for nothing. And here we are assuming all the integers are 4 byte, okay? A counter is 4 byte, great. right? So this is your baseline. Look at the second approach. Second approach is we are going to keep a table, key value pairs. This is your key. This is your value. But we are this time, because we have the key, we are not going to initiate a counter for every pair. We only initiate a counter for the pairs with count larger than 0. Okay. Then we need some overhead for a hash table. So when we are looking at hash tables or dictionaries from the previous slides, we take it for granted. We say we just do key value pairs. So each value will be 4 bytes. This is a counter, right? But if you look closely, we actually need to store the key. What does this mean then? Well, if an integer is 4 bytes, then item ID is 4 bytes, another item ID is 4 bytes, a value is 4 bytes. So a total of 12 bytes for one entry in your key value pair. So Coke, milk is your key, value is the counter. We see it once. This together require you 12 bytes. Okay, this is this approach. But the benefit of doing this is we don't have to initiate your counters beforehand. So why? Let's look at how triangular matrix works here so that you can get a better idea. Triangular matrix looks like this. So what does this mean? You have every items here. You have every items here. This is your Coke, Pepsi, diaper, milk, juice, and so on. This again, Coke, Pepsi, diaper, milk, juice. And each component here represent a counter. So you don't really need this, right? This is counting Coke and Coke, and we don't need that. And what is this counting? This can count the occurrence of Coke and diaper, okay? What does this count? The occurrence or frequency or support of Coke and, oh, sorry, this is Coke and Pepsi, this is Coke and diaper, this is Coke and milk, and so on. So think about this. This is a matrix, but we actually don't use this. Great. But what does it mean, a matrix? So if you have a matrix, to access an element in the matrix, and in this case is the counter, you only need the index, right? So this could be 1, 0, and 0, and you have this item. Oh, we don't use that item. So row 1, column, row 0, column 1, so 0, 1. 0, 1 is the counter for Coke and Pepsi. Okay, so this means we do not really have to store that key value. We don't need to store key Coke and Pepsi. We only need their ID. If their ID start from 0, so 0, 1, 2, 3, 4. Every time we see a C, we know it's ID 0. We will just go to 0 here. And we see P, Pepsi, we know it's 1, so that we will be able to find the location of the counter by using A as the matrix, and 0 and 1, and we can increment the counter, right? This way you don't have to store C and P, so that you only store the counter, which is 4 bytes. What is the drawback of this approach? Well, because you're using index and you're creating a matrix, you cannot really skip any counter, right? You have to create counter for every possible pair. If you skip them, then your index will not work. So for example, if we say we don't really have C and M appear together, so you don't want to allocate this memory space, what do? Can you just squeeze this here? well, then you have to change index for this counter, but you might not want to change index for the remaining of the counters. Okay. So this is called the triangular matrix because we only use this part and we have to initialize a counter for every possible pair. So in this triangular matrix approach, if you have n, that's the total number of item types you have in your store. We want to order each pair of items like this, I and j, so that I is smaller than j. I is the item ID, j is also the item ID, right? So for C and Coke and Pepsi, this ID will be 0, this ID will be 1. Then we can start to keep your pair count in the lexicographic order. 1, 2 first, 1, 3, 1, n, 2, 3, 2, 4, and so on. This means if you think about your triangular matrix, we are actually converting this triangle part into what? A one-dimensional array. And when you are scanning this one-dimensional array, we are actually doing this. Come back to the beginning and do this, and do this, and do this. Right, so you don't really need a two-dimensional array because if you want to find the item, the counter for the pair ij, remember before I told you you can use a, ij to find it. But if you store them in this lexicographic order, you just take ij, you compute the location of the ij. This is the lexicographic order. Based on this scanning sequence, you'll be able to find it. So you have A, and this A is a one-dimensional vector, and this P is calculated by this. Then you have your counter. So why are we doing this? Well, because if you keep using the two-dimensional array, you're going to waste all this space, right? You're not going to use this. So we want to convert this triangle part into a one-dimensional array, and we want to index them. We can index them so that we can find them. All right, great. So the number of pairs that you would have would be n choose 2, approximately this number, approximately 2n square byte if one counter is 4 byte. So triangular matrix requires 4 bytes per pair. So there's a question for this method. We have to count all the pairs to keep the structure of the matrix. Okay, you don't have to count them, but you have to initiate a counter for them. You have to initiate a counter for every pair to keep the structure of the matrix. You will not count them if they will not be there. Yeah, they are the placeholders just to maintain this structure. So think about this. Your method number 1 require 4 per pair, but you will need to initiate a counter for every possible pair. Method number 2 is this key value pair approach. You have C, you have P, and you have a counter. This requires you to use 12 byte per counter, but you only count occurring pairs, right? So that's why it shows that only some pairs you have to count. Others, you don't even have to initiate a counter and you are saving space. So if we compare the two approaches, the first approach require 2n squared byte based on our calculation. This is the same from the previous slides. Approach number 2, the triples, you would need to use 12 byte because you have to store the key, which is a pair, and the value. So there's no best approach, but your approach 2 will be able to beat approach 1 if fewer than 1/3 of the possible pairs actually occur in your basket, right? But if most of the pairs occur in your baskets, then you should use triangular matrix. If fewer than a third, then you can use the second method because it's more expensive for each counter. Okay. How do you know then? Anybody? How do you know? Before you can decide. You're choosing between these two approaches for initialize your counter. How do you know which one you need to use? Okay, so the same, you sample your data. After you sample your data, you try both approach. Well, you can look at how many pairs are in how many baskets so that you can decide. Okay, so it's always about sampling. Take a small sample. So now you have some understanding about the data structure that we are going to use to store your counter. But what if we just have too many items that we need to count, and the pairs, either the triangles or your triples or these key value pairs cannot fit into your main memory? Can we do better? We can. That's your a priori algorithm. This is a very popular algorithm, and we're going to talk about it next time. That's it for today. I hope you enjoyed the lecture. Make sure you read your chapter, start working on your homework assignment. Your TA should respond to your questions on Piazza within 24 hours on weekdays. If they don't, ask again. Well, you don't ask again, but you just put more discussion so that I will know. I will tell them. Start your homework assignment 1, and what else? Oh, read the material, so prepare yourself for the quiz next week. Oh, very important for your quiz. If you submit too late, I think your grader is going to post a buffer again. Too late, that will be 0 points because we have people submit really late, and that's not okay. For your homework assignments, I will need to say this again. Please do not give other people your code. Please do not use code that you find on the internet or from previous semesters. We take this very seriously. You will get 0. We will report it to the university, and it's a lot of paperwork. I don't want to do it. I'm sure you don't want to do it. And the only way you learn is to go through the assignments. All right. Question. A priori algorithm will not be covered next week because we haven't covered it yet. All right. Thank you, everybody.
Thank you.
Do you have
wait.
office hour after that?
Yeah, I do have office hours. So stay if you want to talk to me. Have a great weekend.
Hi, Professor.
Yes.
I have a question regarding the environment setup for the assignment 1.
Okay.
Can I share my screen too?
So just tell me what type of questions you cannot set up your environment on a Windows machine or on Linux machine?
On Mac. So I set up my PySpark can start like appropriately, but when I try to run the sample code on the PPT, it just start to showing up errors for the.
Okay.
Yeah, I'm
that
not.
would be a question for your TA though.
Okay.
The best way to do this is to post it on Piazza's and
Yeah,
have her reply to you.
Yeah. Okay, I will wait for the TA's response.
Okay.
Hi, Professor.
Yes.
I also want to ask a question about the environment setup because I am right now using Mac OS, the Big Sur version, which is not compatible with Python 3.6. So
Okay.
I'm asking if it is okay to use a 3.8 or 3.9 because it really annoyed me a lot.
Okay, so that's actually also a question for your TA because they're going to grade it, right? So I don't know if they're going to use the environment that will be compatible to your environment. So post it on Piazza.
All right, thank you.
Sure. Oh, somebody says you can try use Docker. That's a good suggestion. Thank
What
you.
is Docker?
So Docker is a virtual machine. It's a container. You can just run another machine on your machine, right? So in Docker, you can create a Ubuntu image and just run that, run Spark within that image. Then you should be okay.
Okay, thank you.
Sure. So there's a question, which part of chapter 6 and chapter 3 will require for quiz 3? Well, in general, all the things that we covered. So we covered so far. All right, any more questions? Let me see, participants.
Hello, Professor.
Yes, who is this?
Sorry, what?
Who is this? I don't know who is talking now.
Hi.
Oh, okay, hi.
My first part of question is about the homework. So, because the requirement said we are not allowed to use some external libraries. And my question is that can I use the spark.read.json to load the JSON file? Or
Very good question. You should. That's also a question for your TA on Piazza.
Okay. And the next question is about some basic knowledge part about the Monday course that TA taught us. Let me share my screen. Wait a minute.
Did you guys go to the TA's office?
Yeah, actually, I already got to TA's office twice, and what I did was to fix the environment variables.
Okay.
Yeah, because we need to download once again because the addition is not matched.
Okay.
And yeah, my question is about this. So my question is that how does program connect with the entire Spark infrastructure?
Oh, driver.
Yeah. Like how does Python program to run or connect to the Spark like this?
With the driver code. So driver is a set of libraries that will run as you're in your environment, right?
Yeah.
So you need to start Spark and you need to start the driver, and then you use the driver will help you to connect to the cluster manager and all these different things.
My question is that where did the map function do in this structure?
The driver will assign the map task to worker nodes and reduce tasks to worker nodes. And starting from there, they will run on the entire clusters.
Also, map function is will do on the worker nodes, right?
Right.
Okay. And the next question is about today's lecture, and I got some concept confused. Wait a minute. Can you see my screen now?
Yes.
For baskets and items, it's just like a basket will hold many items. Like the basket is the key and the items are the value.
Well, it's not many items, some items.
Oh, so several items. Okay.
Right.
Okay. And
Because if you think about the supermarket use case, a transaction will not contain too many different item
yes.
types, right?
Yes, that's true. And so the purpose of like so our purpose is to find the highest confidence and highest interest.
No, not the highest. You use a threshold.
Oh
to
yeah,
say
the high
everything that's-
confidence and high interest.
Right. Association rules with high confidence and high interest.
Does high interest include a native or positive or the absolute value?
Well, it depends on your application, but many
Okay.
times you want both.
Okay, got it. And okay, thank you very much.
Sure. All right. Anybody else?
Let me think whether I have more questions.
Okay. Then, Finn, do you have any questions?
No, I'm good. Thank you. Thank you, Professor.
All right.
You have a good weekend.
You too. Zhongwei, do you have more questions?
Yes, I have more questions.
Oh, okay.
Could you mention more about the interest value?
What do you mean? Which part?
Wait a minute. Let me share my screen.
Sure.
Just like today, you mentioned too many concepts, and I sometimes got confused.
That's fine. You probably want to read it first before the
Okay.
class
Okay.
next time.
Yeah, because I prepare for the quiz and prepare for the home assignments. Actually, the environment variables makes me very got me frustrated.
Yeah, I know. It's not easy. It's very confusing.
Yeah. So my first question is that what's the I and the J in how to use this? Could you give me an example?
Oh, that's just the index. That's just the index of the matrix.
Yeah, because you said before is a triangular matrix, and we just like flap to one dimensional.
Yeah, so like here. 0, 1, 2, 3, and we don't need this, we don't need this, right? We only
Yes.
want here. So this one is what? Ij is 1, 1. Okay. And based on I is 1 and J is 1.
1, 2. This.
Oh, sorry, 0, 1. My bad. I is 0 and J is 1, right?
Oh yeah. 0 and 1. Yeah.
And based on the lexicographic order, this is not an algorithm. This is just how you calculate it. It's very easy if you think about it.
So 0 minus 1.
And n minus this plus this and this. N is the total number of items here, right? So this tells you how you would be able to convert this two-dimensional location into a position in this one-dimensional line. This line looks like this.
So suppose n equal to 5 and just like -1 times 5 and plus 1 and minus 0?
I think it might start from 1, 1, but I could be wrong. You can try it.
Okay. So yeah. Actually, the index make me a little bit confused. I do not know whether it start from 1 or start from 0.
Yeah, I think it might start from 1.
Okay. Okay. Got it. Okay. I will try by myself. And yeah, and could you mention more about the interest part? I already know the confidence. What about the interest?
Which part?
Uh,
Which part of the interest?
like to calculate the meaning of interest, like why we need to calculate the interest.
Well, because if this is very high,
Mm-hmm.
it's not very useful, right? If milk is in every basket and you say you find the rule says buying Coke implies buying milk, that's not very useful because we already know that milk is everywhere. So
Okay.
you want to take this probability here. If milk is very everywhere, this number will be high.
So which means if the milk is very high, so buying Coke is not has no relationship with buying milk.
It has relationship. It's just that relationship is not very interesting because milk is everywhere.
Okay. Also, it's not very specific. It's kind of like this.
Well, no, it's just not very interesting. Not very interesting.
Okay.
It's specific. It's talking about this one rule, and that rule is real, right? But it's
Yeah.
just that rule is not very interesting because if you use that rule, it probably will not give you anything.
Okay. Got it. Thank you very much. I will read the article and review this course. Thank you.
Sounds good.
So next quiz it will only include the chapter 6 and the knowledge what you taught this today.
Yeah, everything we covered today.
Okay, got it. Thank you very much. Thank you. Have a
All
good
right. Thank you. Have a good night.
day. Thank you.